Excellent. All right, so good morning, everyone. It's nice to have you guys here, the last day of BlinkOn. Um, my name is Edenilson Cavalcante. I'm based in the San Francisco Bay Area, and I work for the DCAI Data Center and AI Group within Intel. And today we're going to be talking about zlib. How fast can you go? All right, so notices and disclaimers. Your mileage may vary. Owners gonna be lowers. Trademarks are trademarks. But look at the bright side, lowers help to keep us out of trouble, right? Okay, so why should we care about zlib? Well, I checked it yesterday on the Web Almanac. This is the data for 2022. So gzip is still the most popular compression type. It's used by basically 60% of scripts and near 70% of CSS. And under gzip, you have zlib. Broadly is making some steady growth. Maybe in 2 years from now, I would like to spend some time optimizing broadly. But aside the fact that compressed content in the web uses zlib, there is also the matter of PNG images. So near 30% of the images in the web, they use PNG. And under libpng, we use zlib. And even internally, by Chrome, the browser, zlib is used to compress JavaScript source strings to save memory. It's used by Angle to compress traces and compile shaders, and by V8 for what they call snapshots. And what is challenging about zlib is that it runs both inside of, say, the sandbox in the render process, as also in a privileged level as part of the network operations. Cool. So what is the objective of this presentation? Basically, is to share the maintenance work performed in the last 6 months, report some performance improvements, and show some original research leveraging hardware acceleration on 4th generation Xeon processors. We started like 1 month and a half ago. Right, so a little bit of context. Chromium has a patched zlib that uses SIMD optimizations for both x86 as also ARM architectures. So it can be up to 3 times faster than, say, a vanilla zlib for data decompression, and up to 30% faster for data compression. And it's been under active development since 2017. Is almost 6 years already, and is used everywhere, both by Chromium as also Android, Node.js, V8, and since last September by Google proper in the servers. Cool, right. So security maintenance. This is really important because you must have like a really fast software, a really fast core library, but also need to care about the security. Right, so last August, there was a CVE, security researcher discovered that if you have a properly crafted payload and you pass that to zlib, and next to call an API called inflate get header, you could have a buffer overflow. So what I think is fun is that generally I receive those emails generally like Friday night. Then I have to spend my weekend investigating what is happening. Good news are Chromium was not impacted because in the whole code base we don't use this API, right? And the issue was reported on 31st August, and I had a patch done on 20th 3rd August. And we had to backport the fix all the way to M104. And this is what it looks like when, say, we have a XAMPP build, and we have added a new unit test with this properly crafted payload. And basically, without the fix, we would end up having an overflow. that is fortunately patched, and Hans Weinberg, he even added a fuzzer. So thanks to the fuzzer, we could find something similar in the future. Right. Okay. About security. Canonical zlib, which is the upstream zlib, made a release on October 13th. Because we were partially in sync with the development branch of Canonical zlib, we were able to perform the sync relatively fast with just 2 patch sets. Earlier this year, we had a quite challenging sync operation because there was a window of 5 years between the release of zlib 1.2 11, 1.2 12. But because now we are falling upstream closer, performing the sync was much easier. And I'd like to say thanks to Chris Bloom. He's a retired Googler, as also Noel Gordon, Hans Weinberg for reviewing the patches. All right, performance improvements. So we also have done some work towards improving the speed of zlib. So 4 years ago, we had a PMU based at CRC32. CRC32 is a checksum that is performed when you decompress the data to validate if the data integrity is okay. And PMU stands for polynomial multiplication. It's an instruction available on ARMv8 architecture and uses a Barrett transform that was suggested by an Intel researcher, I believe in 2012. The issue though is that 4 years ago, the ARM processors that I tested, they didn't show much of an improvement, sometimes was like a regression. But in 2020, Apple released the DTK, Developer Transition Toolkit. It was like a Mac Mini with a Apple Silicon processor inside. And I decided to test how the PMU code would behave. And the good news were that there was a quite respectful improvement in the data decompression performance. And around this time, regular ARM processors, they also benefited from the optimization. And we were able to land the patch in September this year. By the way, there are 4 Easter eggs on these photos. I will show the first one. Anyone who attended BlinkOn 2013 may remember they gave to us a water bottle, a blue water bottle. So that is exactly sitting in the middle of the table. And the second Easter egg is on the left side where you can actually see the DTK. And the other 2 Easter eggs I will not say, but if anyone decides to look in the slides, they should be able to find it. All right, so this is what it looks like when applied the optimization. As you can see, depending on the input, the data may have different entropy and may have a different result. But for us, specifically, it's really important HML. So for HML was something close to 13% improvement in decompression speed. And basically, even like for compressed content, like the bad data set of files was still okay. Cool. Right. So in last July, I contacted Dougal Johnson. He's a researcher. I asked him about some performance counters code. And suddenly he started to perform some really innovative research in zlib that was covered in his blog. And this chart shows what was the results for varying data inputs of many different zlib forks. But what was really cool is that if you look, say, on the right side of a given group of bars, the green one was for Dougal's fork of zlib. The blue bar was for libdeflate. Libdeflate is a project that was started, I believe, by a Mozilla engineer a couple years ago. They are really fast, but they don't support streaming. And the next bar would be zlib Chromium. So I started looking into Dougal Johnson's patches, and we have started patching, adding his patches on top of Chromium zlib. The idea is that we will eventually reach the same level of performance that he reported. The first patch was using a flatter Huffman table. So zlib implements the deflate algorithm. The deflate algorithm was created in the late 80s by a guy called Phil Katz. He was responsible for a company called PKWare and had a compressor called PKZip. People who are really old, they may remember it. In the late 90s, a specification was created. And basically the idea is that we use LAMP 077 for performing data compression, followed next by Huffman for entropy encoding. So this optimization suggested by Dougal, the idea is that we can avoid some branch mispredictions when we perform lookups for the next Huffman code by using a flatter, bigger root table. That comes with a price. Basically, we have to use 1.9 kilobytes more of memory per inflate state. But again, I mean, if say you just open a Chrome tab, that's going to take what, like 20 megabytes, 30 megabytes. So 1.9 kilobytes is not that much, especially because even like embedded CPUs, they will have at very least 32 kilobytes of L1 cache. The average gains for Haswell was 5%, and for the Cortex X1 was 8.3%, and landed last September. All right, so okay, how can I click there? Oh well, never mind. Well, I mean, this.
You want to click on a link?
Yeah, I want to click, but I cannot see the cursor.
You want to click me?
Okay, cool. Right, so Noel Gordon, he suggested a new multiplicative hash function for...
Of course, that's opening up in a different tab. Okay, one second.
Right.
I'll get you 1 second. This guy? Yeah, that's what we want.
Right. Ah, okay, it's over here. Oh, the image quality is not good, that great. Oh, well. Okay, well, basically the idea is that today we use hardware accelerated hash function that leverage the CRC32 instruction. But we could actually make things way faster by replacing all that code by something that would be portable, right? With the primary advantage, being that the code would be portable. So basically, like a better speed and portable code is always good, right? Cool. So let me see. I should be able to return to the previous tab, or...
Back over here. What's happening? Okay, I see.
Right. Okay. Right. So what is missing to actually land this patch? We have pixel tests. The pixel tests, they generate PNGs. PNGs, they rely on zlib. So when you change the hashing function, use it to keep the hash tables during data compression, the generated PNG is going to be different. So basically, I have to create a rebaselines for all those tests. But what is important is that when you decompress the image, the pixels are exactly the same. right? Cool. Let me see. All right, so let's talk about some really exciting, at least for me, developments that is exploring hardware acceleration for data compression. Cool. So there is the fourth generation Intel Xeon processors. They feature some really cool technologies, such as IAA, in-memory analytics accelerator, as also QAT, quick assist technology, and a few more. So people who are interested in learning more about it can visit the link to the video. So the question I had was, could this be deployed to speed up some operations in zlib? So a little bit of context. First, this is just a proof of concept. This is running on pre-production hardware. So the reported values, they're useful only to compare, say, vanilla versus patched. There's still lots of work before we achieve production-ready code. And these are Xeon, at least for now, these are Xeon-specific optimizations. And I'd like to say some special thanks to Shengfei Zhu and Joel Schutz for sharing knowledge about those accelerators. There's also code. Cool. Right, so a little bit of context. This is basically what we have on Chromium zlib for data compression, data decompression, depending on the inputs. So in average for compression, we are like 21% faster than, say, vanilla zlib. And for decompression, we are around 2.3 faster. Of course, in some cases, we can come closer to 3 times, but that depends on the input. Right. So what would be the numbers when we say we leverage the accelerators on Xeon processors? Right, so these are the numbers. I'm not sure if you guys can see, but basically for some files, we are like almost 200 times faster, right, for compression. For decompression, the average is like 5 times, but we have to remember that Chromium zlib is already 3 times faster, right? So that would be like 15, 16 times faster than vanilla zlib. And specifically for compression, when we make things like 60 times faster, I imagine that could enable some new user case, but especially for servers. Basically, you could perform lots and lots of work using just a single accelerator. And you can have a setup where, say, a single processor can have like 4 accelerators. And you can have multiple processors in a single system, right? So overall, I think it's really exciting, these new technologies. And that brings us to the next steps. So right now, the proof of concept works in a situation where I know the payload size. I have to find a way to handle streaming cases. I also have to do lots of testing to make sure that this is reliable and stable. And finally, I was talking with some Google guys. They mentioned that they have the interest of maintaining what's called like a stable data stream. Basically, they expect that the generated compression of a given content would be a match with a canonical zlib. So we would have to add support for that when we are using hardware acceleration. And we have an issue with the idea of exploring new Xeon features to accelerate zlib. Right, so what are the next steps? Well, I mentioned the other day that when I started working on zlib, I imagined I could get the job done in like 6 months. I'm approaching 6 years work on it. Even using just software, I'm confident we can improve the compression speed in plus 30%. and compression, we have this patch that is on average 30%. I have some ideas we could also push that even farther. In hardware, this is like really early beginnings of the research, but as you just saw, I mean, it has so much potential. I mean, I consider myself privileged to be able to access this pre-production CPUs and start exploring these new exciting features. And as always, patches are welcome. I mean, feel free to submit patches. And with that being said, some acknowledgement is in order. I'd like to say thanks to the Chromium zlib team or Z team. Chris Bloom, he's retired, but sometimes I'll be sending him a message to ask for a review. Noel Gordon and Hans Bensborg, they're like extremely talented engineers. And when I say Z team, it's more like a bunch of highly talented individuals that are doing some volunteer work, because to the best of my knowledge, no one is like officially assigned to work on zlib, which is really interesting because basically we're talking about code that is used by billions of users, but apparently there are no resources to assign people to work on it. Maybe it's because it's part of the plumbing, right? We only care about the plumbing when it's broken. I'd like to say thanks to my Intel teammates, Shenfei Zhu, Joel, Schutz, Thomas, Gustavo, and Daniel. They're my teammates. We have always like interesting conversations. And I'd like to say thanks to the creators of zlib, Jean-Luc Gailey and Mark Adler. Mark Adler has been maintaining canonical zlib for the last 27 years, since 1995. And that is for free. So it's basically like a gift to the world. And I'd like to see more people acknowledging this work. And finally, my family, especially my wife and my daughter, for being so understanding of my zlib obsession. Sometimes I spend my weekends hacking on it, sometimes Friday nights, sometimes some holidays. But overall, I mean, I think the results so far have been pretty good. And that's pretty much everything I had to show you guys. So, questions? Well, I mean, if anyone is interested in actually seeing the thing running, after the talk, we can like find a place and I can show it. It works on my computer. And yeah, that is it.
Oh, did you have a question?
So it's more a question about how the zlib community interacts with its members and how it looks like. I mean, you've mentioned Chromium's zlib quite some time, and here we see that there is the canonical zlib, which is being maintained by Mark et al., so all the folks. But they, at least how it looks, how it sounds like to me, they are going kind of in parallel to each other. Maybe that's my understanding and that's wrong. But I wonder what's missing, who is lagging behind who, and how you deal with actually contributing back
Right.
to the former one, if they actually reply reasonably okay, fast-wise to you, and how it works with dealing with a community that's a small community, but definitely, as you said, it's used by billions, so it's completely relevant.
Yeah, that's a good question. You see, to my understanding, for the last maybe 10 years plus, canonical zlib didn't receive performance or optimization patches from third parties. So we tried really hard to upstream our chains to canonical zlib, but it never really went anywhere. Maybe the primary concern for the maintainer of canonical zlib is stability. And as a result, we have a situation today where we have quite a few forks of zlib. Our own optimizations, specifically the decompression optimizations, they were ported to other forks. As an example, in 2020, some Amazon engineers, they reach out to me. I explain how our optimizations work, and they contribute that to a Cloudflare zlib. And generally speaking, I think that is a good thing because it helps the community. I mean, an ideal scenario would be if, say, we had like, if we could merge all those different forks and have everyone working together. On the other hand, I mean, until that happens, Chromium zlib is open source. And if anyone is like wants to grab some parts and merge with their own stuff, we are totally fine with that, right? I hope I managed to answer the question. Any further questions? All right, so well, thanks for having me.